Hello everyone and welcome to 30 days of DSA challenge, where we will be solving a DSA problem every day for the next 30 days. So this is our day number 12, where we will again solve a problem based on Q, and the level of this question is going to be hard. So this is the first hard question which we are solving in this series. The name of this question is sliding window maximum. You will get this question link in description, and you can also download this Excel sheet from description. Now, without wasting much time, let's see our question on LeetCode. So this is our question on LeetCode. It says you are given an array of integers nums. There is a sliding window of size k, which is moving from the very left of the array to the very right. You can only see k numbers. You can only see k numbers in the window each time the sliding window moves right by one position. Return the max sliding window. So the question says that we have given an integer array named as nums, and we have also given an integer variable named as k, which is nothing but the size of our window. And every time our window is getting slided from left to right by one position, and we have to find out the maximum element, right? We have to find out the maximum element present in a particular window. So this is our question, and this is a sample test case. So let's analyze this problem by taking some examples. Okay, so this is the test case which was mentioned in the question. This is nothing but our nums array, and here we have the value of k. This k is nothing but the window size. Okay, so now let's analyze what question was about, right? What question is about. So we are having a window, right? We are having a window of size equal to k, right? And in the window we will have some elements, let's say 2, 3 and 5, right? And we have to find the maximum element present in this particular window. So let's say the maximum element is 5. You can clearly see this, right? Now this window will be get right shifted by 1, right? And again we have to find the maximum element present in that particular window. So let me just do this. Let me just do a quick dry run. So let's say we have one variable named as I, which is initially pointing at 0, and we have another variable named as j, which is pointing to 2, right? And this 2 is nothing but it is k minus 1, right? It is nothing but k minus 1. So this is our present window, right? This is our present window, and we have to find the maximum element present in this particular window. So you can clearly see that the maximum element is nothing but 3, right? The maximum element is nothing but 3. So we will have an answer vector or an answer array where we will be storing all the maximums, right? So we'll store this maximum in our array, right? Now what we will do, we will move to right by one position, right? We will move our window to right by one position, right? If I move my window to right by one position, so see, initially my window was starting from I equal to 0, right? From index number 0. But now, as I said, I will move my window right by one position. So now this I will point to one index ahead, which is nothing but index number 1. So now my window will start from this index, right? And we know that the size of our window is going to be 3, right? It is going to be 3. Therefore, we also have to increase our j, right? We have to increment it. So now my j will also point to the next index, which is 3. And now this is my present window. So this was my previous window starting from index number 0 up to index number 2, and this is my new window, which is starting from index number 0 and it is ending at index number 3, right? Again I have to do the same thing. Again I have to find out the maximum element which is present in this particular window. So you can clearly see the maximum element is nothing but 3 itself. So I will add this 3 into my answer variable, right? Now I have done this. What's the next task? I will again move my window to right by one position, right? So now I will increment my I. So now my I will point to index number 2, right? And similarly my j will point to the next index, which is nothing but 4, right? And now my next window is going to start from index number 2 and it is going to end at index number 4, right? So this is my new window, right? This is my new window. Again, I have to do the same thing. I have to find out the maximum element present in this particular window. You can clearly see the maximum element is nothing but 5, right? We have -1, 3 and 5 in this particular window, and the maximum element is 5. So I will just add this 5 into my answer vector. So I will add it here, right? I will simply add it here. After doing this, I will again do a right shift by 1 position. So currently my I is pointing at index number 2, so it will get incremented, and now my I will point at index number 3, right? Similarly, the value of j, you can say the value of j, it will also get incremented, because we have to make sure that the size of our window is equal to k, right? So I will again increment my j. So now my j will point at index number 5, and my new window will be nothing but this, from index number 3, starting from index number 3 and getting ended at index number 5, correct? So this is my new window. This is my new window, and the elements are -3, 5 and 3. Again, the same task, find out the maximum element present in this particular window. You can clearly see the maximum element is nothing but 5 itself. So I will add 5 into my answer vector. And after doing this, I will again move my window to the right position by 1. Okay. So right now my I is pointing at index number 3. So it will get incremented. And now my I will point at index number 4. Similarly, my j will also get incremented, and j will point at index number 6. Correct? Now the new window is starting from index number 4. It is starting from index number 4, and it is getting ended at index number 6, right? So this will be my new window, correct? This will be my new window. And again, we have to do the same thing. Again, we have to find out the maximum element present in this particular window. So we have 5, 3 and 6, and the maximum element is nothing but 6 itself. So we'll add 6 into our answer vector. After doing this, again, we will do the same thing. We have to move our window to right by 1 position, right? To right by 1 position. So now my I will point at index number 5, and j will point at index number 7, right? Index number 7. And my new window is going to start from index number 5, and it is getting ended at index number 7. So this is my new window, and the element present in this window are 3, 6 and 7, and I have to find out the maximum element. So the maximum element is nothing but 7. So I will add 7 into my answer, correct? I will add 7 into my answer. So now you can clearly see that this was the last window, right? This was the last window of size 3. If I again increment the value of I and the value of j, then j will go out of bound. So this was our last window, and this is the final answer, right? This is the final answer. These are the maximum elements which are present in every particular window of size equal to 3, right? Size equal to 3 in this particular array. So this is the question. I hope now the question is clear into your mind. And now let's think about how we are going to solve this. Let's think about the approach, how we are going to approach this particular problem, right? Okay. So if we talk about the brute force approach, then the very first thing which comes in our brain when we see this problem is what we have to do. We have to traverse each and every window, right? We have to traverse each and every window. And in each and every window, I have to find the maximum element, right? These are the two tasks. These are the two tasks which I have. Firstly, I have to traverse in each window. And secondly, I have to find the maximum element. These are the two things which I need to do. Okay. So what I will do, I will use two variables. Firstly, it will be pointing at index number 0. And I will have j, it will be pointing nothing but k minus 1, right? It will be pointing to k minus 1, right? It will be pointing to k minus 1, so that this will be our initial starting window, right? This will be our initial starting window. Okay. So now what's the next task? The next task is to find out the maximum element present in this particular window. So what I can do, I can do a linear traversal, and I can find out the maximum element present here, right? So let's say I did a linear traversal and I found out the maximum element is nothing but 3, right? It's nothing but 3. Okay. Now what I have to do, I have to move my window to its right by 1 position. And how I'll do that? Very simple. I will increment the value of I. So now my I will point at index number 1. Similarly, I will increment the value of j. So now my j will point at index number 3. Right? I'm sorry. j will point at index number 3, and our new window will be starting from here, that is index number 1, and it will be ended at here, that is index number 3. Again, I will do a linear traversal and I will find out the maximum element present. Present in this particular window, right? In this particular window. So I hope the brute force approach is clear. And if we talk about the code of this brute force approach, then it is going to be very, very, very easy. So what do we need? We just need a answer, you can say answer vector or a answer array to store our answer, right? Then we will be needing some couple of variables such as I, which will be initially pointing at index number 0, and j, which will be pointing at index number k minus 1. And we will need a maxi variable, which will be initially it will hold the very minimum value, right? You can either say minus infinity or you can write it as int min, right? Int min. Okay. Now what we want to traverse into our windows, right? We want to traverse into different windows. So for that we will use the I and j. So I can write while j is lesser than n, right? And this n is nothing, it is nothing but the size of our nums array, right? It is the size of our nums array. Okay. Now what we have to do, we have to find out the maximum element, and we will find out the maximum element by doing a linear traversal, right? Before that, I will again just give the maxi value as int min, right? Why I am assigning it int min again? Because when this while loop will get executed again, right? When it will get executed again, then the maxi should get initialized with minimum value, right? That's the reason. Now I want to do a linear traversal. So I can do this with a for loop. I will initialize, let's say int p is equal to I, and p will go up to the value of j. And in the maxi, I will store the maximum element. So maxi is nothing but max of maxi and nums of t, right? Nums of t. So after this for loop, right? After this for loop, I have done my linear traversal, and the maximum element is now present in this maxi variable. So I will just store it into my answer variable. So I will just write answer dot push back if I'm using a vector, right? Push back maxi, right? After putting the maxi value into our answer, we have to do I++ and j++, right? We have to do I++ and j++, so that we will get shifted to the next window, right? Now let's say initially I is pointing at 0 and j is pointing at 2, and the initial value into the maxi variable will be int min. So after doing this linear traversal, the value present in maxi is going to be 3. So we will store this maxi into our answer variable, and then we will increment the value of I and increment the value of j, right? So after incrementing, my I will point at index number 1 and j will point at index number 3, right? And again this while loop, again this while loop will get executed, right? It will get executed again. So if I do not assign int min again, then here in my maxi variable 3 will be stored. And now in this linear traversal, we will try to find out the maximum. We will try to find out a maximum element which is greater than 3, which is wrong, right? Which is wrong, because we have to find out the maximum element only in that particular window, right? Therefore it is important to give int min value again to this maxi variable, right? So I hope this is clear. If you have some doubts, please do a dry run on the same example, then you will understand it in a more better way. And this is the very brute force and simple approach. I hope you understood this. Now if we talk about the time and space complexity, so the time complexity is going to be O of n into k approximately. Why so? Because here you can see that I'm running a loop from 1 2 3 start. So here you can see that I'm running a loop, j is lesser than n, and the value of j is going to be initially k minus 1, right? So j will traverse from this k minus 1 up to the end, right? Up to the end. So you can say approximately it is equal to the value of n, right? Value of n, which is nothing but the size of our nums array. And here we are running again a for loop to do the linear traversal, and it will cost us k, because how many times this for loop is going to run? It is going to run for each and every window, and the size of our window is equal to 3, right? Therefore, the time complexity is going to be O of n into k, right? Now let's talk about the space complexity. So here we are just using one answer variable, which is nothing but a vector or an array. Now let's talk about what will be the size. What will be the size of our answer variable? So see, in our answer vector, what we are storing? We are storing the maximum values for each and every window. So the size of this answer variable will be nothing but the number of windows, right? Number of windows we are having into our array. Now, how we will find out the number of windows, right? How we will find out the number of windows? So see, we can find out the number of windows with the help of I, and we can also derive a formula for that, right? So see, initially the value of I will be at 0, and what will be the last value of I? So the last value of I will be at here, right? At index number 5. So what are the number of windows we have? We will have 1, 2, 3, 4, 5, and 6. We will have 6 number of windows, right? We will have 6 number of windows. So how we got this 6? So see, we have this n, which is nothing but the size. So let's analyze what's the size. 1, 2, 3, 4, 5, 6, 7, and 8. So we have size equal to 8, and the value of k is nothing but 3, right? The value of k is nothing but 3. So n minus k, what is it? It is 8 minus 3, which is equal to 5, right? Which is equal to 5. And what is the number of windows? Number of windows is going to be 6. So 5 plus 1 is equal to 6. So the space complexity is going to be O of n minus k plus 1, right? This is going to be the space complexity for this particular solution, because here we will have total of n minus k plus 1 number of windows, and this answer variable will be storing the maximum element for every window. So the size of this answer variable, it will be nothing but O of n minus k plus 1. So I hope this brute force solution is clear, and if you try to submit this code on LeetCode, you will get a TLE. So we have to optimize this approach. So now let's think about how we are going to optimize the previous solution. So the time complexity of previous solution was O of n into k. And when I say let's optimize, so optimizing means what? It means to reduce the complexities. That is either to reduce the time complexity or to reduce the space complexity. So now let's try to reduce the time complexity. So see, currently time complexity is O of n into k, and if I say to reduce, so let's think about, can I reduce the time complexity from O of n into k to O of n, right? That is, can we solve this problem in a linear time complexity? So this is our new task which we have to do, correct? Okay, so see, in our previous solution, the time complexity was n into k, and the reason why the time complexity was n into k, because we were using a while loop, and inside the while loop we were again using a for loop for doing the linear traversal and for getting the maximum element from the present window, right? So in order to solve this problem in O of n or linear time complexity, we have to eliminate this for loop. So we have to think for a data structure which can store the window elements for us, and it can store the window element in such a way that I can find out the maximum element present in my current window in a constant time, right? So this is my requirement. I have to look for a data structure. I look 1, 2, 3, start. So I have to look for a data structure which can store all the window elements and which can give me the maximum window element present in O of 1 time complexity. So this is the task. Now let's think about that data structure, how we can do that. But before that, let's understand what is our requirement, right? Let's understand our requirement. So see, initially my window would be this, right? And the elements would be 1, 3, and -1, right? Now when I do a right shift, then my window would start from index number 1 and it will go up to index number 3, right? Now the newer elements of this new window will be nothing but 3, -1, and -3, right? So this green window is nothing but my previous window, and this yellow window is nothing but my new window. Now see, whenever we are doing a transition from our previous window to the new window, let's analyze which elements are common in both the window, and also let's analyze which elements got added into my newer window or which elements got deleted from my previous window, right? So see, this 3 was present in my previous window and it is present in my current window as well. This -1 was present into my previous window and it is present in my current window as well. But this 1, right, this 1, it was part of my previous window, but it is not part of my current window, right? So you can say kind of we have deleted this 1, right? We have deleted this 1 to get our new window, right? To get our new window. Okay, but in our new window, we have one element such as this -3, which was not earlier present in my previous window. So you can say that we have added, right? We have added something, right? I have added something at the end to get my new window, and I have deleted something from the front, right? I have deleted something from the front of my previous window to get the newer elements, right? To get the new window, right? Let's analyze it again with one more example, right? So that you will understand it in a more better way and the concept will be clear, right? The concept will get clear into your head, right? Let me just rub this. Okay. Okay. So let's say my current window is starting from index number 1 and it is going up to here, that is index number 3, right? And the element present in my current window are 3, -1 and -3, right? Now when I do a right shift, then my new window will start from here, that is index number 2, and it will go up to here, that is index number 4. And the element present in this new window are nothing but -1, 3 and 5. Now again, let's analyze the same thing. Which elements are common, which one got added, which one got deleted. So see, this -1 was present in my previous window and it is also present in my current window. This -3 was also present in my previous window and it is also present in my current window. But if you clearly see, this 3 was part of my previous window, but it is not part of my current window. So you can say that I have done a deletion, right? I have deleted this 3, right? I have deleted this 3. And from where I have deleted, from which side? So you can say that from front, right? From front, I have deleted this 3, right? I have deleted this 3 when I did a right shift to get the new window, right? I hope it makes sense. Okay. But here we have one element named as 5, which was earlier not present in my previous window. But from somewhere it got added into my newer window, right? It got added into my window. So you can say that I have added this 5. And at which side, where I have added? So I have added this 5 at the end, right? I have added this 5 at the end, right? At the end of my previous window. See, this is our previous window, which have just -1 and this -3, right? Now I have added this 5 at the end, right? At the end to get the new window. So I hope it is clear. Let me just take one more last example and then what I'm trying to say, it will be clear into your head. Then we will think about the approach, right? Then we will think about the approach. So let's say this is my current window, which is starting from index number 2, and it is going up to index number 4, right? So that we can have a window of size equal to 3, right? And the element present in this window are 3, -1, -3 and 5, correct? Now let's say I did a right shift. When I did a right shift, then my newer window will start from here, that is index number 3, and it will go up to index number 5. It will go up to index number 5, right? And the element present in this new window are nothing but -3, 5 and 3, right? So now again, let's analyze which elements are common, which element got deleted, which element got added, right, into this new window. So see, this -3 was also present in my previous window and it is present in my current window as well. Similarly, this 5 was present in my previous window and it is also present in my current window. But if you clearly see, this -1 was present in my previous window, but it is not present in my current window, right? This is my current window, so it is not present in my current window. What does it mean? What does it mean? It means that I have done a deletion, right? I have done a deletion. From which side? I have done a deletion from the front of this window, right? To get my newer window, correct? Again, if you see, this 3 was not part of my previous window. It was not part of my previous window, but it got added. It got added. So I have done an addition, right? I have done an addition. Now, at which side I have done the addition? I have done the addition at the back. At the back. So I hope that now you are able to identify this pattern, that whenever I am doing a right shift, right? Whenever I'm doing a right shift, I'm doing a deletion from the front, right? I am doing a deletion from the front and I'm adding one element at the back, right? I am adding one element at the back. So this is our requirement, right? So see what we were wanted, right? We wanted a data structure in which we can store all the elements of our window, right? And from here we analyzed, or you can say we have observed that whenever I'm doing a right shift, then the element from the front got deleted and one element at the back got added, right? Got added. Now in order to store our window, I need a data structure in which I can do deletion from the front and also I can do addition, right? I can do addition from the back, right? So we need this kind of data structure, and that data structure is nothing but a Deque, right? That data structure is nothing but a Deque. See, in Deque, I can do a deletion from front, right? I can do pop front. It means that I can delete one element from the front and I can add an element from the back as well, right? I can do push underscore front, right? So I can push elements or I can add elements from the back. Sorry. This will be back, push underscore back, right? It means I can push elements or I can add elements from the back. Not only this, in a Deque, see, not only this, in a Deque, see, from the front side, I can do pop, but I can also do a push operation, right? I can also do a push operation from front. It means that I can add elements into my Deque from the front, right? Similarly, from the back as well, I can do push underscore, sorry, I can do pop underscore back, correct? It means that I can delete elements, from back as well. So this is the data structure which we will be using to solve this problem efficiently. Why we are using this particular data structure, I hope it is clear into your mind, because we need a data structure where we can do pop from the front and where we can do push operation from the back. So whenever we are moving to the right, we can update our window, right? So I hope this thing is clear. Now let's move ahead. So see, previously what we were doing in the for loop inside while loop which we are using, see, in the previous code we were using a while loop, and inside the while loop we were using a for loop, right? And what was the use of this for loop? So this for loop was used to kind of linearly traverse into our window and to get the maximum element, right? So see, now what we have done here, we have stored all the elements, window elements, current window elements into our Deque, right? But what I want the maximum element. And very importantly, I want the maximum element in a constant time, right? In a constant time. So I also have to think of it, how I will get the maximum element in constant time from this Deque, right? So to solve this, what we will do, we will store elements into this Deque in a descending order, right? In a descending order. So firstly, at the front of our Deque, we will have the maxi, or you can say the maximum element, and at the end we will have the minimum element, right? We will have the minimum elements. So let's say in our Deque we will store something like this: 5, 4, 3, 2, 1, right? In the descending order. So here this 5 is nothing but it is our first maximum element in the present window. This 4 is the second maximum, this is the third maximum, this is the fourth maximum, and this is the fifth maximum, or you can say the least or the minimum element. So we will store in this format, so that I can directly from the front I can directly get the maximum element, right, in constant time. So right, so this is the approach which we will use. This is how we are going to store elements into our Deque. So I hope this is also clear. Now let me just do a quick dry run so that you will understand it in a more better way. So let's say we are running a loop, and this is the I iterator, which is initially pointing at index number 0. Okay, so see, how we are going to store elements into our Deque is clear. We want to store in the descending order. So firstly we'll have the maximums, and at the back we will have the minimum, right? At the back we will have the minimums. See, initially my Deque is empty. It means I don't have any element present into my Deque. So should I add this one or not? The answer is yes, definitely I should add this one. I should definitely add this one. Now, when I have added this one, right, it means that I have just one element present into my Deque, and this one is itself the maximum element, and it is in itself the minimum element present in our window as well, right? I hope it is clear. Now what we will do, we will increment the value of I. So now my I will point at index number 1. Now this is very important, right? This is very important. See, I had explained you that we will store elements in this order, right? In this decreasing order, right? So let's say I have stored this one here. And I know that I want to store in decreasing order, right? So where I can add this 3? See, I cannot add this 3 here, because here I should write the elements which are lesser than 1. Correct? Okay. But I can add this 3 before this one. Right? Yes. Probably I can do that. But in the question, it was clearly mentioned that I want the maximum element. So see, the previous maximum was 1, but now I got someone who is greater than 1, right? Who is greater than 1, who is nothing but 3. Now, just ask yourself that can this one be my possible answer? This one can be my possible answer or not? So the answer is no. This one cannot be my possible answer. Why? Because I have already got someone who is greater than 1, right? And in order to get the maximum element will be either 3 or someone who is greater than 3, right? Or someone who is greater than 3. So see, now we know that we do not have to do anything with this 1. It cannot be a possible answer. So does it make sense to store it into my Deque? The answer is again no. I should not store it, because this will not be my answer. So why should I store it into my Deque? Correct? So therefore what we will do, we will delete this one, right? We will just simply delete this one, and we will add this 3, right? We will add this 3 because this is our new maximum, right? This is our new maximum. Okay. After that, what we will do is we will again increment our I, and now my I will point at index number 2, right? My I will point at index number 2. Now, the element present at index number 2 is nothing but -1, right? The element is nothing but the -1. So see, this is the way I should store elements into my Deque, and I have already stored this 3 here, right? And now I'm getting this -1, which is lesser than 3. So where should I add? Where should I write this -1? At the front or at the back? So see, here I cannot add -1 because then this decreasing order will not be satisfied. So it means that I can only add this -1 at this side, right? After this 3 only I can add this -1. Correct? Okay. So what I will do, I will just add this -1 at this particular position, right? At this particular position. Now, you may ask me one question, that we had just deleted this 1 because it could have not been our possible answer, because we got someone who is greater than 1, who is 3, right? Now, if we just apply the same, just the same concept, then we have this 3 and we have this -1, and we want the maximum element. So why should I store this -1? Because I already have 3, and the maximum answer will either be 3 or someone greater than 3. Possibly any value which is lesser than 3 cannot be a possible answer. So why should I store this -1 here? So there is a reason behind it, right? Let's say instead of having 3 here, if I had -3 here, right? Instead of 3, if I had here -3, and if this was my present window, right? If this was my present window, then you can clearly see that this -1 is the maximum element present in this particular window, right? This -1 is the maximum element present in this particular window. Or let me just give you one more example. Let's say that instead of having, let me just give you one more example. Yeah, so let's say in this particular window, instead of having 5, if I had -5 here, then again you can see the maximum element is nothing but -1, right? -1. So this is the reason why we have to store this -1. And it was also, right, I told you that I am going to store elements in such a form that initially I'll have the first maximum, then I will have the second maximum, and then I will have, you can say, the third maximum, and then I will have the minimum element at the back, right? At the back. So this is the reason why I am storing an element which is lesser than the maximum element, right? Which is lesser than the maximum element. Okay. So now see, here the value of I is at 2. It is at 2. And this is nothing but my first window. This is nothing but my first window. So I have to store the answer, right? I have to store the answer. Now, from where I will get the answer? Very, very, very simple, because I already explained you that at the front I will have the maximum element. So at the front, what is the element? Element is 3. So I will just directly add it into my answer. So let me just write it here. So let's say this is our answer vector. So I will directly add 3 here, right? I will directly add 3 here, correct? And after doing that, I will increment the value of I, correct? So now my I is pointing at index number 3, and the current window is nothing but this, right? This is my current window. So see, when we are making a transition, whenever we are moving to the right by one position, then I have to make sure that in my DQ, all the elements which I am storing, they are part of my present window, right? This 3 should be part of my present window. This -1 should be part of my present window. I have to check whenever I'm doing a right shift. I have to check. I have to definitely check. Okay, but how I can do that? Because see, here I am storing the elements, right? Here I am storing the elements 3 and -1. I have no clue how I can get this, that these particular elements 3 and -1 are part of my present window or not. So instead of storing the elements, if I store their index, right? Let's say instead of having 3, if I have the index of 3, which is nothing but 1, and instead of having -1, if I store the index of -1, which is nothing but 2, right? So here let me just write the elements which are present at this index. So at index number 1 I have 2, and at index number 2 I have -1, right? So at index number 1 I had 3, and at index number 2 I had -1. Okay, now I have to check that these indexes are part of my present window or not. So how I can check this? I can check this. See, I know that the size of my window is going to be equal to 3, right? The size of my window is going to be equal to 3. And my I is currently pointing at index number 3. So if I do I minus k, right? If I do a I minus k, it gives me 0. Now what does this 0 signifies? This signifies that this 0 index is not part of my present window, right? It is not part of my present window, and all the indexes which are lesser than 0 are also not part of my present window, correct? So now I can clearly see, I will calculate I minus k, which is equal to 0, and I will check, is this 0 or any element which is lesser than 0 is present in my DQ or not, right? So I can clearly see that we do not have any element, we do not have any index, sorry, which is lesser than or equal to 0 into my DQ. It means that my DQ is storing the correct elements. Okay. After checking that in my DQ I am storing the right elements or not, I will see what is the element present at this particular index? It is -3, right? It is -3, right? And in my DQ, currently the elements are 3 and -1. They are 3 and -1. It means that I have this 3 and I have this -1, and I got this -3, right? I got this -3. Now, where should I add this -3? Where I should add this -3? I should definitely add it at the back. I should definitely add it at the back, so that this decreasing order will get maintained. It will be maintained. And when we were doing a dry run, when we were thinking about why we need DQ, then I also told you that whenever we are moving a right, whenever we are doing a right shift, I'm doing an addition at the back, right? I'm doing an addition at the back. Therefore, we will simply add it at the back, right? We'll simply add it at the back because it is lesser than this -1. It is lesser than this is -1. And if it is lesser than -1, if it is lesser than -1, then it will come after. It will come after this -1, right? Therefore, what we will do, we will add this -3. So as I told you, we'll not add the element, we'll add the index. So we'll add this 3, and let me just write this -3 here for the reference, right? Now, after doing this, again, we will check in this particular window what is the maximum element. So how I will get the maximum element? I will get the index of the maximum element from the front of my DQ, which is nothing but 1. And the element present at index number 1 is nothing but 3. So I will write this 3 here, right? I will, let me just rub and write it again. So I will write this 3 here, right? So I hope this particular thing is clear. This particular thing is clear. And after this, what I'll do, I will again do a right shift. So now my eye will point at index number 4, right? My eye will point at index number 4. And the window size will be this, right? The window size will be this. Now again, I will check that in my DQ, I am storing the correct indexes or not. I am storing the elements of the current window or not. So how I will do that? Very simple. I will do I minus k. The value of I is 4 and the value of k is nothing but 3. So I'll get this 1. Now what does this 1 signify? This 1 signifies that this one is not part of my present window, right? This is not part of my present window. So I will come into my DQ. And I'll check. Do I have this 1 present into my DQ? You will say, yes, it is present. So I will delete this. Right? I will simply delete this, right? And after deleting, now I can say the indexes which are 2 and index which is 3, they are part of my present window. So they can be stored into my DQ, right? Okay, no problem. So now we will see what is the element present at this particular index. So the element is nothing but 5. So see, where we have to store this 5, right? We have to think about it. So let me just delete this. So see, currently in my DQ, what are the elements? They are -1 and -3. Okay, I have this -1 and I have this -3 and I got 5. I have to add 5 here, right? So I have to think about, where should I add 5? Should I add 5 here? Should I add 5 here? Should I add 5 here? Or should I add 5 here? Where should I add so that the order is maintained? The decreasing order is maintained. So what I'll do, I'll compare this 5 with the last element. And what is the last element? Last element is -3. I will check which is the maximum. This 5 is my maximum. What does it mean? It means that this 5 is greater than this -3, right? And what I want the maximum element. So now this -3 is not of use for me, right? Because I want the maximum element. This -3 cannot be a maximum element. So why should I store it into my DQ? So what I'll do, I'll just remove it. I will just remove this, right? I will just remove this -3 here from here, right? Now I will again compare this 5 with this -1. Right? I will see what is the maximum, 5 or -1. You will say the maximum is 5. And what we have to return? We have to return the maximum element. So if I got 5 which is greater than this -1 and I have to deal with the maximums, then is this -1 is of use to me? You will say, no, this -1 is of no use for me. So what I'll do, I will again delete it. And after doing all the deletions, I will finally add this 5 into my DQ. I will finally add this 5 into my DQ. So this is what I will do. So I will delete this, and I will add 5. So instead of adding the element, I will add the index. So I will add 4 here, and here I'm writing the element which is present at the index number 4, which is 5. Okay. After doing this, we know that this is again my one window. Again, I will check the maximum element. How I'll get the maximum element? The index of the maximum element will be stored at the front of my DQ. So here I have 4, that is index number 4, and the element present at index number 4 is nothing but 5. So this 5 is a maximum element. So I will just add it into my answer, right? I will just add it into my answer. And after adding it, I will increment the value of I, right? I will again increment the value of I. So now my I will point at index number 3, right? And my present window will be this, right? My present window will be this. So again, I have to check that in my DQ, I am storing the right elements. I am only storing the elements which are of my current window or not. How I will do that? I will just do I minus k. So which is nothing but 5 minus 3, which is equal to 2. It means that this index 2 or the indexes which are lesser than 2, they are not part of my present window. So this 2 should not be present in this DQ. So I will check, is this 2 is present into this DQ? So we'll say no, this is not present. So I'll not do anything. Okay. After doing that, I will see which element is present at index number 5. It is nothing but 3, right? It is nothing but 3. And in my DQ, I have this 5. And this 3 is already lesser. It is already lesser than this this 5, right? So I have 3 which I have to add, right? So where I should add it? Should I add it here or should I add it here? It is very simple. I already told you, whenever we are doing a right shift, we have to store the elements at the back. We have to add the elements at the back. And the other reason is I have to maintain the descending order. Therefore, I will add it after this 5. Right? So instead of adding the element, I will add the index, which is 5. And here, let me write the element which is present at the index number 5. Okay. Again, this is my current window. So I will try to find out the maximum element, and the index of the maximum element will be present. The index of the maximum element will be present at the front, which is nothing but 4. And the element present at index number 4 is nothing but 5. So again, I will add this 5 into my answer, right? And after doing this, I will again increment the value of I, right? So let me just do this. Here we had 3. Okay. So now my I will point at index number 4. Sorry, it was, I think, already present here, right? So now we will increment the value of I. So let me just remove this first. Okay. So now my I will point at index number 6, right? My I will point at index number 6. Okay. So now when I am at index number 6, I will again perform this I minus k to check that in my DQ I am storing only the right elements or not. So this is my window. So I will do 6 minus 3, which is equal to 3. It means that this 3 and all the indexes which are lesser than 3, they are not part of my present window, right? Okay, so I will check, do I have 3 or any index which is lesser than 3 present into my DQ? So you can clearly see that we do not have any index which is 3 or lesser than 3 into my DQ. So I do not need to do any deletions from the front, right? Okay. Now we will see which element we are having at this particular index. So here we have this 6. And let me just see what all elements I am storing into my DQ. So see, in my DQ, I have stored this 5 and 3, and I have this 6 which I have to store, right? Where I should add it? I should add it at the back, right? Because whenever I am doing a right shift, I am adding the elements at the back. But if I add it here, then this descending order will not get maintained, right? It will not be maintained. So I have to again do something, right? So I'll do some comparisons, right? I'll compare in 3 and 6, what is the maximum? So you will say the maximum is 6. And what I have to return? I have to return the maximum element. So does this 3 can be my answer? This 3 can be my answer or not? So the answer is no, it cannot be my answer. It can never be my answer because I want the maximum and 6 is maximum. 6 is greater than 3. So I will just delete it. I will just delete it, right? Now I will again compare this 6. Now I will again compare this 6 with this 5, right? What is the maximum between 6 and 5? You will say the maximum is 6 itself. The maximum is 6 itself. So again, just ask yourself. So see, previously I had this 5. I had this 5 and I got 6, which is greater than this 5. So now, can this 5 be my answer? Can this 5 be my answer? So the answer is no, it cannot be my answer because I want the maximum. I want the maximum. So I will also delete this. I will also delete this. Now, after deleting all this, I will finally add 6 into my DQ. It will indicate that this 6 is the maximum element present in that particular window. So let me just delete this. And I will add 6. So instead of adding 6, I will add the index. Index is also 6. So I will store it here, right? And now I want the maximum element present in this particular window. So the element which is present at the front, right? The index which is present at the front is 6. And the element which is present at the index 6 will be my maximum element. So I will add 6 here. And after doing this, I will again increment the value of I. So before that, let me just remove all these things. Okay. So again, now the value of I will be at index number 7, right? So again, I will check that in my DQ, I am only storing the relevant elements or not, right? I am storing only the indexes which are part of my present window or not. So I will do this I minus k. So I is 7 and k is 3. So here I will get 4, right? I will get 4. What does this 4 signify? It 4 signifies that this index 4 and all the indexes which are lesser than 4, they are not part of my present window. So the index 4 and the indexes which are lesser than 4 should not be present into my DQ. So I'll check, do I have 4 or any index which is lesser than 4 here? You will say no. It means that I do not need to delete anything. Then I will check what is the element. Again, I will check what is the element present at index number 7. It is nothing but the 7 itself. Okay. So in my DQ, see, presently I have 6. And I got 7. I have to add this 7. Where I should add it? I should add it at the back. But if I add it at the back, then this descending order will not get maintained. It will not get maintained. Okay, then I'll see what is the maximum between 6 and 7. So the maximum is 7. So again, ask the same question to yourself. What do we want? We want the maximum, right? We want the maximum. And we have maximum as 7. Now, can this 6 be my answer? So the answer is no. This 6 cannot be my answer because I want the maximum. I want to return the maximum. So what I'll do, I'll just remove this 6, right? And after removing the 6, we have nothing present here. So I will directly add 7 here. So instead of adding the 7, which is the element, we will store the index of 7, which is again 7. So I will write 7 here, and the element present at index number 7 is again 7. So this is one of my window. So again, I will get the maximum element from the front, right? So from the front, I will see the index number is 7. So the element which is present at index number 7 is the maximum in this current window. So at index number 7, we have 7 as element. So I will add it into my answer, and this will be my final answer, right? This will be my final answer. And after this, if I increment the value of I, it will go out of bound. So this is the approach. I hope it is clear. And if you have doubts, then I recommend you to do some dry runs, do 2 or 3 dry runs by yourself. So now I hope the approach is clear. And now let's think of how we are going to code this particular solution, this particular approach which we have discussed. So what do we need? We need a vector, right? We will need a vector to store our answer. So let's name it as answer, right? And we will also need a DQ to store the indexes of our present window, right? So let's name it as Q, right? And after that, what do we need to do? We need to do a normal traversal. So I can do this from this while for the blah, blah, blah. Okay. So 1, 2, 3, start. So now let's think of how we are going to code the solution or the approach which we have discussed. So what do we need? We need a vector to store our answer. So let's name it as answer. And secondly, we will need a queue data structure to store the indexes of the present window, right? So let's name it as queue. Let's name it as queue. And after that, I can just normally do a normal traversal in my array. So I can use a for loop int I from 0 up to it is lesser than n. And this n is nothing but the size of our nums array, right? Nums array. So what's the first thing which I need to do? So let's say that I am here in this particular window, right? I am here in this particular window. So firstly, I have to make sure that in my DQ, I have only the indexes which are part of my present window, right? Only indexes which are part of my present window. So how I can do this? How I can do this? So I can just write if not of queue dot empty. So firstly, I have to check that my queue is empty or not, right? It should not be empty, right? And the second thing is I will just check if this queue dot front, right? If this queue dot front is lesser than or equal to I minus k, right? If this is the case, then I will pop out elements from the front. So I will do queue dot pop front, right? So I will pop out the element from the front side, okay? And after doing this, what is the second task? What is the second task? So see, whenever let's say I'm adding this 5, so I have to think of what is the correct position. Where should I add this 5, right? Where should I add this 5? So for that, what we will do, we will run a while loop. We'll see while not of queue dot empty, right? While my queue is not empty, and queue dot back, right? So see, in the queue, what we'll have, we will have the indexes, right? We'll have the indexes. So I should write nums of queue dot back. If it is lesser than the current element queue dot I, just do queue dot pop back, right? Just do queue dot pop back. See, whenever I am getting an element which is greater than what I have previously in my DQ at the back, I'll do pop. And after doing this, at the end, I can directly add the element at the back, right? So I will write queue dot push back the index I. And after that, I also need to store my answer, right? So here I can just write answer dot push back the nums of queue dot front, because at the front I will have the index. And I also need to write one thing: if my I is greater than or equal to k minus 1. And this is our code. Now you may question why I have written this I is greater than or equal to k minus 1. So see, let's say initially my I is here at index number 0, right? So see, in this window I have just 1, but in the question it was mentioned that the window size should be equal to 3. So is this window is equal to 3? You will say no, it is not. Okay, so I will not store the answer, right? Again, my I will get incremented and it will come at index number 1. So now this is the current window which is of size 2, but I should have the window of size equal to 3. So I will again not store the answer because this is not the correct window, right? This is not the correct window size, right? Now the I will get incremented and it will come at index number 3. So now you will see that this is a window size equal to 3, which was mentioned into our question. So now I will store the maximum element, right? And now if the value of I is equal to 3, then this will be my window. So this is again a valid window of size equal to 3. So again, I will store the maximum element into my answer. So this is the reason. So I hope this particular approach is clear to you. And if we talk about the time and space complexity, so the space complexity is going to be similar. It is going to be O of n minus k plus 1, because here we are using this answer variable, and at max we can at max we can have 1, 2, 3, and at max in our answer variable we can have elements equal to the window size, right? And this is nothing but the window size. And if we talk about this DQ, then the space complexity of this DQ will be equal to K, right? It will be equal to K, because at max in my DQ, I can only have all the indexes of my present window, right? At max. And if we talk about the space time complexity, then the time complexity is very simple. It is going to be O of n approximately. So now we are here on LeetCode, and the coding portion is going to be very easy. What do I need? I need a vector of int to store my answer. Then I will need a DQ. Let's name it as Q. And then I will simply run a for loop. Int I is equal to 0, I is lesser than nums dot size, and then I plus plus. Okay, so here firstly what I need to do, so I need to remove indexes, right? I should say indexes which are not part of my current window, right? Which are not part of my current window. How I can do this? Very simple. I'll write not of q dot empty, right? Not of q dot empty, and q dot front, right? Q dot front is equal to I minus k. If this is the chance, I just need, if this is the case, sorry, I will do pop dot front, because I want to pop the elements from the front, right? And then what we need to do, if I got a higher value, right? If I got a higher value, then I need to I need to pop out from backside, so I'll write while not of q dot empty, and nums of q dot back, q dot back is lesser than my current element, which is nums of I, then I'll do q dot pop back, right? I will do q dot pop back. And after doing all this, I can just simply add that particular index into my DQ. So I'll write q dot push back I, and after that I will check if my I is greater than or equal to I minus 1. That means this is my one proper window. Then I just need to push it into my index, push it into my answer. So here I will write nums of q dot front, because in our DQ we are just storing the indexes. And after doing this, I think we are done. We just need to return our answer, right? So let me just run this. So you can see that all the sample test cases are running fine. Let me just submit this. So you can see that this particular solution is accepted. I had also explained you the time and space complexity. So this was all for this day, and I hope you liked this video. If this video was helpful for you, do like this video, share it with your friends, comment down your experience if you are facing any issue in coding. If you are facing any issue in coding this particular solution, right? And if this video was helpful, make sure that you subscribe to this channel, and we will meet again tomorrow with a new question.